Okay, we're into the final topic for the year, atoms and nuclei, and we're going to look at the first subtopic in this topic, and that is the structure of the atom. So, by understanding the structure of the atom, amongst other things, it lets us understand all about light, and how light is produced, and how some of the different sorts of light that you're familiar with are produced. We're also going to hopefully get a bit of an understanding as we go along how important that this understanding the structure of the atom is in basically what we'd call the analytical science. And that can range from looking at the composition of distant stars to analysing water and mineral samples for certain elements that we might be seeking, or certain impurities in the water that we might be trying to make sure don't exist. So this topic is called the structure of the atom, but it's going to seem more like it's about light than the actual structure of the atom. But hopefully as we go through this, you'll see that basically it was the light that was emitted or absorbed by atoms that really allowed us to work out what the structure of the atom was and give us the model of the atom that we use today. And still, in many ways, when we want to analyse atoms, we actually analyse the light given off by atoms, because obviously atoms are very, very, very small, and we can't just, if you like, look at individual atoms, but by analysing the light that they give off, we are able to determine a lot of information about them. So let's learn why that is the case. So if we take a hot gas, which might be in the case of a fluorescent tube, or it might be one of our vapour lamps that we've looked at in the lab, or we'll look at in the lab if you haven't already, and we look at that through a spectrometer, we will see a pattern that looks something like this. And we call this a line emission spectrum, or a line spectrum. We see a series of individual little bands of colour, if you like, which represent the wavelengths or the frequency of light emitted by this gas. So a hot vapour of pure element emits light at discrete frequencies, resulting in the line emission spectrum when it is viewed through a spectrometer. So the other key word here is discrete. So each atom will emit a different set, or a different line emission spectrum, so a different set of coloured bands. So why is this the case? Well, the presence of discrete frequencies in the spectra of atoms is evidence for the existence of discrete energy levels in the atoms. So when an electron makes a transition from a higher to a lower energy level in an atom, the energy of the atom decreases and is released as a photon. The energy of the emitted photon is given by the energy difference between the two bands equals HF. It goes on to say that, and that gives us F, the frequency. So it might be easier to look at this in terms of the diagram here. Okay, so let's look at it in terms of this diagram here. If we excite the atom, so basically we can push it from what we call the ground state. So all the electrons are in their lowest energy state. So they're all in the base orbital, if you like, from the chemistry sense. When we put some energy in, an electron jumps up into a further out orbital, is how you can sort of think of this if you're familiar with the chemistry model. So we can excite the atom here in red, and we can either do this using heat, or you can also use a voltage, or basically electricity, and that causes the atom to jump up into a higher state. Then after that atom jumps up into a higher state, fairly soon after, it will relax back to the ground state. When it relaxes, it'll release a photon of light, and the energy of that photon will basically equal the E2 level here minus E1, which is equal to, in this case, minus 13.6 minus minus 3.39. So basically the difference in this case, the delta energy, because we're not really worried about the sign, is equal to 10.21 electron volts. So if we know that energy, we can use the formula E equals HF to work out what the frequency of that formula would be. And we could also work out the wavelength. So if I just show you that briefly here, if we know delta E equals H times F, so if we know delta E, we know Planck's constant, we can rearrange that, and we can get frequency equals delta E on H. So we could work out the frequency of that photon. One thing we do need to do before we do that, obviously, though, is that's in electron volts. So we need to convert that into joules. And remember, we do that by timesing by 1.6 times 10 to the minus 19. So make sure you convert that into joules before you substitute it into this formula here. Obviously, we can also, if we don't want to know the frequency, because quite often we want to know the wavelength, we can use the formula delta E equals HC on lambda. We've talked about where that comes from before. Remember, basically the wave equation tells us that C equals F times lambda, so F equals C on lambda, and that's basically been substituted into that equation there. Then if we rearrange that, we get that the wavelength equals HC on delta E. So we can work out what wavelength would be emitted if an atom was excited into that state and then relaxed and released this photon here. I reckon that's pretty straightforward calculations for you guys to do now, so, and because I'm running out of room, I won't go through and try and do all that. So there's only one atom we really need to know about in detail for this course in terms of the structure and the energy levels of that atom, and that is hydrogen. And that's represented by the energy level diagram that we've got here. And in particular, what you need to know is about basically the three series of lines that you'll see when you look at the spectrum of atomic hydrogen. And we'll do this in the lab. We'll use a hydrogen globe, which will excite with a high voltage power supply, and we'll look at the lines through the spectroscope, and you should see at least some of these lines. There's some we also won't see, and we'll talk about that a little bit later on too, why. So firstly, when we excite the hydrogen, the atom then obviously relaxes and it releases light. And we can get this first series, which is where the atom relaxes all the way back to the ground state. And this series here would have obviously the greatest energy, and they would therefore also have the greatest frequency because E equals HF, so they're proportional to each other. And they will all have the least or the smallest, I think we'll go with the word smallest, wavelength, because wavelength is inversely proportional to frequency. And in reality, these are all in the UV region of the spectrum, so we can't actually see them with our eyes. And they are referred to normally as the Lyman series. Then, the next series that we see all finish in the N equals 2, so that, if you like, first excited state above the ground state. And they all correspond to the atom going from those energy levels there. So all of these are the ones that we can actually see. So these are in the visible. So when we look at this in the lab, these are the ones that we can actually see. So they're the visible region, and they're known as the Balmer series. And they basically look like this one, which is similar to what you'll see through the spectroscope. This is our Balmer series. And the final series that we need to know about for this course are the ones that end in the n equals 3 level, so the third level. They come down to here. So they will have the least energy, so therefore the least frequency. Therefore, they will have the greatest wavelength, and these will be in the infrared region of the spectrum, and they are known as the Paschen series. I don't actually think you need to remember Lyman, Balmer and Paschen, but you do need to remember which ones are in the UV, which is the ones with the greatest energy, smallest wavelength, the visible, which is the in-between ones, and the infrared ones, which have the least energy, therefore the least frequency, therefore the greatest wavelength. And finally, for this section, you need to have an understanding of what the ionisation energy is. And the ionisation energy of an atom is the minimum energy required to remove a single electron from the atom in its most stable or ground state. So, if we have the hydrogen atom here, and we have an electron sitting down here in the ground state, if we want to knock that electron right out of the atom to make it form an ion, we have to put in that much energy there. So in this case, 0 is defined as the starting point, and we come backwards, so that means that we would need to put in 13.6 electron volts of energy to excite an electron from the ground level, so that would have just enough energy to basically get kicked out of the atom. So this is almost going back to what we talked about with the photoelectric effect. If you had hydrogen in the ground state and you were shining light on it to excite them, and typically, obviously this would need to be UV light, it wouldn't be visible light, that would be the minimum amount of energy you would need to knock an electron out of that atom.